We're going to work through some practice problems solving systems of equations using the substitution method. And remember, when we're solving a system, like our goal is to find the values of x and y that make both equations true. And we call that the solution to the system. So just to clarify, like any x and y that makes a single equation true is the solution to the equation. So for example, in this first equation, y equals 2x, well, I know that when x is 0, y is 0, so that is a solution to the equation, but it's not a solution to our system, because if I plug that into my other equation, 0 plus 0 does not equal 12. So we're looking for the unique solution that is true for both equations. So when we do this with substitution, generally we want one of our variables and one of our equations isolated. So I notice that in this first equation, y is isolated, meaning it's all by itself. And in the moment where both x's and y's are equal in both equations, we could just swap out our two y's because they're both y and they're both equal. But in our top equation, we know y is equal to 2x. So that also allows us to swap or substitute 2x for y in either equation. So it would be helpful to swap it into the bottom equation. And that's helpful because that will generate an equation where only x is the variable. So instead of writing x plus y equals 12, I'm going to write x plus 2x equals 12. Out of habit, I put 2x in parentheses. When we substitute, we usually do so in parentheses, but there's nothing out in front, so I could just drop them. I don't have like a multiplier or a negative to distribute. So when I combine my like terms, x plus 2x is 3x. And if 3x equals 12, I can divide both sides by 3 and get that x is equal to 4. So now I have found half of my solution. We found the x value that should be true for both equations. So we also need the y value. And we could plug this into either equation, but we have one that says y equals 2x. That seems like the easiest one to use. So if y equals 2x, when x is 4, y equals 2 times 4, which is 8. So this should be our solution, but we have a way of checking to make sure our answer is correct before we move on. Let's use my other equation. So if I take the equation x plus y equals 12, if we plug both the values of x and y in that we just got, we should see that they work. So if x plus y equals 12, well, if x is 4 and y is 8, that should equal 12, and they do. So our solution to our system is 4, 8, or x is 4 and y is 8. And if we were to graph these two equations, 4, 8 would be the point where they intersect. All right, let's look at just a couple more, and then we'll look at a few special cases. So in number 2, for example, 2 and 4 are really similar. Actually, let's look at number 4. In number 4, I notice that I don't have a y isolated, but that x is isolated in one of my equations. So it doesn't matter which variable we're substituting for. So since I notice that x is isolated and I have an x in my other equation, I could take this expression 4y plus 1 and replace either x with the expression 4y plus 1. So it would be helpful to do in the equation at the top. So I have my 2, but instead of putting x there, I'm going to substitute for x 4y plus 1. So the equation I just wrote is the same as the equation at the top, but instead of x, we substituted 4y plus 1. So now I have, this one's a little more difficult to solve than the first example, but I can distribute that 2 to get rid of the parentheses. So I get 8y plus 2 minus 3y equals 12. And then I could combine some like terms. So like 8y minus 3y is 5y. And from here, we just follow the steps of solving using inverse operations until we find what y equals. Okay, so y equals 2. So remember, we're not done. We also need to find x. So I like to use this equation since x is already isolated. So if y equals 2, I could substitute 2 for y into this equation. So we get that x equals 9. And then lastly, don't forget that we have the power to check our answer. So since I know that 2 and 9 will work for values of y and x in the bottom equation, I'm going to double check using the other one. So 2x becomes 2 times 9 minus 3y 3 times 2 equals 12. So 18 minus 6 equals 12, and that's a true statement. So I know that my solution is correct. So my ordered pair would be 9, 2, because remember we write x then y, not necessarily the order in which we found our solution. Okay, I'm not going to work all of these out, but in number 3, for example, just to kind of help us, actually, let's look at number 3 to help us get started. I notice that we have 2 equations where y is isolated, and in each equation we have a different expression for y. So the substitution that we could do is just replace one of our y's with one of the other expressions. So I could write 2x minus 5 equals 4x minus 7 when I substitute 2x minus 5 for the other y in the other equation. So now I have an equation where everything is in terms of x, and so I might subtract 2x from both sides as a step towards solving. We would have negative 5 equals 2x minus 7. Then add 7 on both sides. Then divide everything by 2. So we get that 1 equals x, or x equals 1. So now it doesn't really matter which equation we use, whichever one you think looks easiest. If I plug 1 in or substitute 1 in for x in my top equation, I get y equals 4 times 1 minus 7. Oops, 4 minus 7 is a negative 3. And I can just check in my bottom equation, do those both work out? So if y is negative 3, the right-hand side is 2 times 1 minus 5. It checks out. So both x and y make both equations true at the same time, which is why that is our solution. So 1, negative 3. All right, so if you are working through these, you might notice when you get to the last 2 questions, something kind of funny happens, something different happens. So let's look at number 7. In number 7, we have an equation where y is isolated. So I know that in my other equation, I could substitute the expression 6x plus 4 for y. So let's try that. So I'm rewriting this equation, except when I get to y, I'm not writing y there. I am substituting, remember the parentheses are really important, 6x plus 4 into that equation. So now I do have to mind my parentheses because I have subtraction before them. I could think of there as being like plus a negative 1 there. So I do need to distribute that negative to eliminate my parentheses. So that is going to make a negative 6x and a negative 4. All right, so now as we're solving, as we combine our like terms, 6x minus 6x, Well, those things undo each other. I get 0x. So I get 0 minus 4 equals negative 5. And that's the same as saying negative 4 equals negative 5. And that might cause us to pause. Like, I might start to think that I have made a mistake because I got rid of all of my variables. Like, all of my x's went away. I got to this statement that says negative 4 equals negative 5. And that's not even true. Like, that doesn't even make sense. But the thing is, we did not make a mistake. So when this happens, and we get a statement here that is false, we know negative 4 does not equal negative 5. So when we get to that statement where it says negative 4 equals negative 5, but that's not true, what that means is that our system has no solution. And if we want to understand that a little bit better, we could manipulate this top equation. If I were to solve this for y, so maybe I add y to both sides, so like negative 5 plus y, and then maybe I add 5 to both sides to get y by itself. So 6x plus 5 equals y, or I could write this y equals 6x plus 5. What we might notice is that if I were to graph this equation and this equation, well, they have the same slope, but different y-intercepts. So like one of them starts at 4 and has a slope of 6. The other one starts at 5 and has a slope of 6. I'm just drawing that by hand, a sketch. But if I graph two lines that have the same slope and different y-intercepts, they're going to be parallel lines, meaning that they're never going to intersect, meaning that there is no x and y value that makes both of those equations true at the same time. That's why our system has no solution. All right, let's look at number 8. Again, I have y isolated in one of my equations, so I could substitute 2x minus 8 for y in my other equation. So 6x minus 3 times 2x minus 8. All right, so I've got to be careful here. When I distribute, I want to think of that as a negative 3. So I could either rewrite it as addition, like 6x plus negative 3, or just think of it as a negative 3 when I distribute. All right, so we get 6x minus 6x plus 24 equals 24. So as we can see, something similar happens here. 6x minus 6x is 0. And we get this statement that 0 plus 24 is 24. And that's true. So this is really similar to what happened in number 7. But in number 7, we got a false statement. This statement is true. 24 does equal 24. So what in the world does that mean? Well, when this happens, this actually means that we have infinitely many solutions. And again, let's think about the graph of this. Let's say that I solved this for y. So like maybe I subtract 6 from both sides. And then maybe I divide everything by a negative 3 there. Oops, I forgot. I lost my x somewhere. Where did, oh, that was 6x. Sorry, maybe we subtract 6x from both sides. So I get what, 2x minus 8. And what I notice is when I solve this equation for y, well, it turns out that it's actually the same equation as the one above it. So if we were to graph both of these equations on the coordinate plane, well, they would be the exact same line. So like if we start at negative 8 and have a slope of 2, just kind of sketching a graph here. If that's one of my equations, the other equation would lie completely on top of it. So any solution that makes one of the equations true makes them both true, and that's why they have infinitely many. So for example, Let's say that I plugged in 0 for x. So if y is 2 times 0 minus 8, I get y equals negative 8. So 0 comma negative 8 is a solution to the system. But what if I plug in 1 for y, or for x rather? So y equals 2 times 1 minus 8. So 2 minus 8, which is what, negative 6. So 1, negative 6 is a solution. And there's infinite solutions. I could plug in decimals. I could plug in 0.37 for x and use a calculator and find y. So any ordered pair that lies on one of those lines will lie on the other, and every ordered pair represented by the lines is a solution to that system of equations.